So it's time to talk about polymers. Polymers are pretty interesting compounds, as noted by this quote that I stole from somewhere, but I can't remember where, and it's been too long since I stole it. But physical properties of polymers are what make them interesting and useful. First of all, what the heck are polymers? A polymer is a large molecule made by linking repeating units of small molecules called monomers. So here's a little cartoon. There's a bunch of monomers, little small molecules, go through a polymerization process, and you hook them all together, these little black dots, little black lines, connecting them all together now. That's a polymer. It's a big macromolecule. Polymers and macromolecules have very different properties than their small molecule, even monomer counterparts. I teach a class, an upper-level chemistry class, all about polymers, but polymers is a very large, wide area of chemistry and engineering even, a very large area of study. We're going to give you the briefest of brief overviews of what polymers really are and why they matter at this point in your organic journey. There are two main groups of polymers, synthetic polymers and biopolymers, or natural polymers. Things like DNA, things like RNA, things like proteins, peptides, things like oligosaccharides, the big cellulose, those big things. I can't think of the one. Cellulose, a big oligosaccharides, a bunch of sugar molecules connected together, whatever you call those things. Those are all biomolecules, biopolymers. They're synthesized by our cells. Synthetic polymers are synthesized by people. Some of the synthetic polymers that you may have heard of are PET, that's plastic recyclable number 1, sometimes called PETE actually. We've maybe heard of high-density polyethylene or low-density polyethylene. That's things like your plastic bags, low-density, or high-density, your milk jugs, lots of things. We've maybe heard of polystyrene. Polystyrene is in a lot of stuff. That's PS. PVC is one we've actually even mentioned in this class before. Synthetic polymers, that is not an exhaustive list whatsoever. It's not even close. But synthetic molecules are made by people. Synthetic polymers can be called plastics, but plastics officially are polymers that can be extruded. So not all synthetic polymers are actually plastics. There are lots of synthetic polymers that are being investigated in medicinal purposes now. Those are not necessarily extruded polymers. They're not necessarily plastics. Okay, so in the classes of synthetic polymers, there are two main pathways to obtain a synthetic polymer. There are step growth polymers, also known as condensation polymers, and there are chain growth polymers, also known as addition polymers. Step growth polymers look like this first figure. This first figure is step growth polymers. You have a bunch of monomers. Some of them hook up like this and this and this, and then some of those chains hook together, and then some of those chains hook together, and eventually you build a giant macromolecule out of that. Step growth polymers are often much shorter chains than chain growth polymers. That's little details that you don't need to know, but sometimes I nerd out on polymers because I like them. I think they're very interesting. We're going to get to what you need to know in a minute. Hold on. Chain growth polymers is the other broad category that we'll talk about. Why are we talking about it now? Because some chain growth polymers involve free radical processes. There are other polymers that are chain growth that do not go through free radical processes, but some of them do. So we're going to talk about the ones that do. Here's a table from your textbook. It's in a chapter way ahead of where we are under specialty topic organic things. I mentioned a couple of these polymers already. Here is ethylene. If you polymerize ethylene, we might call it polyethylene. Polyethylene is I need to refresh my statistics. It's one of the most commonly used plastics in the world. All extruded plastic bag type things are polyethylene. Trash bags, grocery bags, Ziploc bags, all kinds of stuff like that. There's high density, low density. I've already said that, but we're not going to talk about the specifics there. But it could be hard plastics or flexible plastics, all kinds of stuff. We also mentioned PVC in this class before. It's vinyl chloride that you polymerize to make polyvinyl chloride. It's in a lot of stuff. Polypropylene, it's a big plastic, big plastic polystyrene. Believe it or not, red Solo cups are made out of polystyrene, but so is styrofoam. The difference in the styrofoam and red Solo cups are how the extrusion process works. Again, it's real specific to polymers. We're going to get into it in our upper level class, not in here, but I'm just trying to tell you that polymers are pretty interesting. This guy, polymerize him, you make Teflon, nonstick coating in your frying pans. Yeah. Acrylics, all kinds of acrylic things, rugs and yarn and stuff, fur. Plexiglass. Yeah, the biggest plexiglass sheet in the world is at an aquarium, Monterey Bay Aquarium. If that polymer didn't have the properties that it did, those sharks would not be retained by that plexiglass wall. Yeah, polymers are kind of interesting to me. Why should you care about them at least for a little bit longer is because some of them can be polymerized through radical mechanisms. Now to where you really should care. This is styrene. This molecule is styrene. If you polymerize styrene, you make polystyrene. What happened when styrene polymerized? The pi bond went away and it became a single bond. The CH got connected to the CH2 of the next polymer in the line, the next monomer in the line. The CH got connected to the CH2 of the next monomer in line. The CH got connected to the CH2 of the next monomer in line. The way polymers are drawn is the repeat unit is enclosed in brackets like this with a little N on the outside of that bracket. So that tells me that unit is repeated a lot of times in order to make this polymer. Depending on how many times it's repeated, you get a lot of different properties out of the polymer. Okay, so some polymerization processes are radical processes, like this one below. AIBN, aza-bis-isobutyronitril, this guy, that's a radical initiator. Are you ready to draw this radical polymerization mechanism? Whew, let's do it. So if I start with AIBN, it's a big thing. AIBN is this guy. When you expose AIBN to heat or light, it can initiate a radical thing. This one said heat, so I'm going to put a little heat on it. The initiation process goes like this. Yep, all those, all at once. And what we get out of it, in the center, we made nitrogen gas, an N triple bond N, nitrogen gas. Those nitrogens already have lone pairs. And we made this, oops, that's crooked, and this radical out of that initiation. What's cool about AIBN being used to initiate reactions is nitrogen gas is volatile, so it escapes out of your reaction chamber as a gas, and you're left with those two radical cyanide thingies, radical nitrile thingies, as your radicals, your only radicals in the solution until, sorry, this is initiation. I should have written that already. Until that reacts with one of your monomers. So if we react that guy with our styrene monomer, tell me, is the styrene more stable to have a radical here or more stable to have a radical there? Is it more stable to have a primary radical or a secondary and benzylic radical? Hopefully you shouted at your computer that it's more stable to have a secondary and benzylic radical. So we do like that. We get this thing connected to the CH2 that was our styrene, and we made a styrene radical there. That then begets a bunch of propagation steps. That styrene radical I'm going to call this stuff R. And I'm going to say R, CH2, and then my styrene radical. Reacts with another styrene, and I'm going to go crazy on colors down here because I'm drawing it like it's a cascade. I'm going to draw it like it's a sort of cascade reaction, but it's not like this. It's iterative. It's propagation again and again and again and again and again. We're almost done with the crazy colors. It's propagation again and again and again and again, but I'm going to draw it like it's not. I'm going to draw it like it's a bunch of these hooking on all at once. It happens like this. It would really, truly make a styrene radical on that blue benzoic carbon there. But I'm not going to draw it like that. I'm going to keep on going because what would happen to that radical is it would add to the orange one, and that's going to add to the green one, and that's going to add to the red one, and then we do end up with a red radical there. Okay? I cheated and paused and erased all that top stuff so that I could draw my colorful polymer up top. I've got this R, that was where my AIBN joined in. I've got a new bond created there, a new bond created here, a new bond, and a radical. So this is my polymer, but that chain, this chain where that radical is there, that chain could propagate to continue to grow and grow and grow until you run out of monomers. A lot of other side reactions could happen, but again, that's for an upper level polymer class. The predicting the product of a radical polymerization is what you need to worry about. And so that's this thing. Let's pretend it terminates with another AIBN over here. So if we erase that dot and we put on another R group to terminate our radical, there's our colorful polymer chain. How are you expected to draw this polymer? You should draw the monomer as given. You should erase the double bond of your alkene. You should extend a long arm from one side of your alkene, a long arm from the other side of your alkene, and encase the entire thing in brackets. Put me a little N, tell me that thing is repeated again and again. Can't you see that that's all this is? It's this thing repeated again and again and again. Every different color is a new monomer unit that's got long arms coming out the side of that bracket where it's connecting to the next monomer. Yep. All right. So in addition to being able to predict the product of polymerizations, you need to be able to recognize which of the following might occur through a radical process. So you're really looking for initiators. What are radical initiators? We've seen peroxides as radical initiators. That was peroxides and light, peroxides and heat. AIBN, we just saw, was a radical initiator. AIBN and light, AIBN and heat. Which of the following can occur by radical processes? This one, for sure. AIBN and light, yes. This one, for sure. Peroxide and light, yes. The bottom one is not a radical polymerization. It can still be a polymerization, though. It's officially a cationic polymerization. Yeah, okay. We do need to be able to draw the products of these polymerizations. I draw my given compound. I erase the pi bond. I extend long arms where I broke that pi bond. Make sure that kink is visible right there. And I encase the whole thing's in brackets. I need to kind of try that one again, maybe. That looks much more traditional zigzaggy right there. My kink in the middle kind of disappeared right there. This guy. It's polyvinyl chloride, PVC. Yeah. The next one. I draw my polymer. Draw my alkene, my monomer. I erase the pi bond. I extend long arms. I really don't like how I draw these. The bonds are terrible. And I put it in brackets. If I give it more zigzag to it, that's what I really want to do. That's my polymer. That's the acrylonitrile that we saw previously. Yep. This cationic polymerization, it can also polymerize. It does so like that. This carbon, this carbon is that carbon, and there should be 2 methyls on that carbon. There are. And a CH2. Look, there is a CH2. Yep. So you need to be able to predict polymer products. You need to be able to recognize which kind of polymerization is a radical process. You need to be able to give the structure of the monomer from which the polymer came. All you got to do is take those long arms and fold them back inside. This is not curved arrows up here. This is just me trying to show you with arrows what I would be showing you with my hands and my arms if I could. This is the monomer that polymerized to give me that polymer. My alkene here came from folding in the 2 arms that I've unfolded on all those previous questions. Fold in those arms, I get this monomer. You have to be able to predict the polymers and predict the monomers and tell which are radical processes. A couple more things, really just very tiny little things, because I think polymers are cool and I want you to think polymers are cool also. Everything we've talked about so far are homopolymers. That's one monomer creating a polymer. But you can take multiple monomers and mix them together and make what's called copolymers. So if you took something like vinyl chloride and vanillidine chloride, you get saran wrap. Yeah. If you take acrylonitrile, 1,3-butadiene, and styrene, you get ABS. ABS is something that are in a lot of car parts. Keyboard parts are made out of ABS plastics. Copolymers, you see how this world gets pretty wide pretty quickly? Everything we just drew that could make a homopolymer, you could put it with something else and make a copolymer, and you get totally different physical properties out of it. Ugh, I can totally nerd out. This is not a copolymer example, but it's related in a way that we have 2 alkenes in this molecule, so those 2 alkenes can polymerize. If I have some sort of radical initiator, I'm drawing this like it's going to happen like a cascade, and it doesn't really. If I have some sort of radical initiator, that radical initiator can do this and start this whole polymerization process for this diene. Oh boy, oh boy. Yeah? All those green arrows I just drew, what's happening is we're going to have a green radical initiator over there, and it's going to terminate somehow on the other end. We end up with this pi bond and that pi bond breaking. Those 2 pi bonds fold out to make my arm here and my arm there. Those 2 middle electrons fold together to make a new pi bond across this top flat bond. That new top flat bond. Yeah. This is isoprene that polymerized to make this compound. Just because I think it's cool, when I have unsaturations in this compound, that makes the polymer much more flexible. This is natural rubber. This is a flexible polymer because of the unsaturations. It also needs to be a Z double bond because an E double bond is more rigid and stiff than a Z double bond. Ugh, who would have thought? All this chemistry really is real world applicable. Why am I showing you? I'm showing you if you polymerize a diene, one of the alkenes still stays, or you shift where it is, but you still keep an alkene in your polymer product. Okay. Neoprene is one of the most famous examples of polymerizing a diene. 1,3-butadiene, 2-chloro. If I polymerize that thing, that's how I get neoprene. If I were drawing it, it's got to be that cis-like configuration. I'm going to put long arms out the two sides, like so. That new pi bond in the middle was created. There's my polymer that is neoprene. Wetsuits are made out of neoprene. Yeah, cool stuff. So polymers can be measured for their crystallinity, and you get different properties based on that. You can cross-link them to make them stiff or not so stiff. You can change their glass transition temperature if you want them to be kind of liquidy at room temperature or not, or whatever. You can recycle a lot of them, not all of them, a lot of them. Some of them are biodegradable. Some of them have medicinal purposes. They're being used to deliver drugs to patients with targeting properties. They're used in some wound healing things. They're all over all kinds of medicinal purposes. It's not just the big six plastics that are causing a lot of environmental issues these days. Polymers are everywhere. They have very tunable properties, so they're used in lots of things. Yes, we use a lot of plastics, but they're used in a lot more than plastics. That's all I have to say. See ya.